Hey guys, I'm just continuing straight on from the previous video. So we saw that a good place to start was 2 N32 bars. We now need to verify this by making sure that the tension in the steel equals the compression in the concrete. This case will exist because we have pure bending. So we just need to check this. This is the same as the yield stress of steel times the area of steel needs to equal alpha 2 FC dash. That is the stress component of the concrete over here. Times by its area would be A times by B effective. Okay, so A times B effective is the area. So rearranging for A, we get this formula over here. We know alpha 2 is 0.85. So just subbing everything in, we're going to get the yield stress of steel is 500 MPa. The area of the steel, we've got 2 N32 bars, so it's 2 by pi by 16 squared. Divided by alpha 2 is 0.85. Times by FC dash, the strength of the concrete is 32 MPa. Times by B effective. So B effective from back here is 1150. So continuing on, we can solve for A, and if we do that, we can find that A is 25.7 millimeters. Alright, so we're going to be using this value now. That is the depth of the rectangular stress block, is 25.7 millimeters. So just to show you where we're at, we're now going to be finding the capacity moment and checking that against the design moment. So we need to check that M, the capacity moment, is greater than M star, the design moment. Now, just to remind you, we're going to be taking moments about this point here for the tension steel. So the moment's going to be the tension in the steel times its lever arm, which is D minus A on 2. The tension in the steel is the same as the area times its yield stress outside of its lever arm, which is D minus A on 2, must be greater than M star. And again, we are ignoring the reduction factor phi. So subbing in for everything, we assumed 2 N32 bars, so we're going to be doing 2 by pi by 16 squared is the area, times the yield stress, times the the yield stress of steel, 500 MPa, outside of D. D was 597 minus A on 2. A